Last time we started a discussion on the exact vector modes in a step index optical fiber. Right, so these LP modes that we solved for are approximate modes, but they work very well in the weakly guiding approximation when the index contrast is very small. Right, but the exact solution for any general fiber are actually these EH and HE modes, right? So right, so as we discussed last time, the way to exactly solve for the mode profiles is to first solve for Ez and Nz, right? Because the Z component is, or the Z unit vector is invariant, so we can use the scalar wave equation, right, for Ez and Nz. And so we can solve in the cylindrical geometry in the same way, and then we saw that, for example, we can write right, so we can write Ez as something like right, so the same kind of solutions that we found for the LP modes, but in the LP modes we were solving for the transverse components, right? Here we are solving for the longitudinal component, and we get the same kind of solution because we use the same equation, right? And for Xz, for example, right? So again, we'll get two indices, L and M, right? So L comes from the azimuthal part, right? It's integer 0 and 2, and then M is the mth for the transcendental equation. When we solve, the mth solution gives the index M. Right? And so then we said that, so this relation between the amplitudes of electric and magnetic fields, A and B, are also given by the transcendental equations, right? And so we get different cases. So, for example, if L is equal to 0, then the transcendental equation forces either A to be 0 or B to be 0. So, in case A is 0, then you can see that means Ez is 0. Right? So, this would be a TE mode, a purely TE mode, because the longitudinal component of E is 0. Right? So, these are denoted as TE0M modes. And if B is equal to 0, then they are TM modes. Right? Because the magnetic field is purely transverse now. But for any non-zero L, in general, both Ez and Hz are non-zero. But depending on the relative magnitudes, so again, two cases. So if the magnitude of A is bigger than B, which means the electric field longitudinal component is dominant over the magnetic field, we call it the HE mode, right? So this will be HELM, right? So this is closer to a TM mode because the longitudinal part of the electric field is stronger compared to the magnetic field. And then the other case will be EH, which is closer to a TE mode, but not purely TE or TM. Only for L equal to 0 are the modes purely TE or TM. Right. So then we said that we can find the other components, like so for example ER, E5, HR, H5 from the solutions for Ez and Hz. Right. So using the Maxwell-Curl equations, we can write each of those four field components in terms of just Ez and Hz. Right. So we have terms like, for example, so ER or something like this. Right. So using these expressions, we can now write the other field components. Right. So now, for example, you can see so ER has a derivative of Ez with respect to the radial coordinate. Right. So we get a derivative of the Bessel function here. And we've seen these relations, right? So, like for example, for the Bessel function, we have these relations like the derivative. So recall we had relations like these. So right. So basically, the derivative takes the Bessel function to a higher or lower order by 1. Right? So we'll get if we use this identity here, so we'll get terms where now we are having Bessel function of either higher or lower order depending on whatever sign we choose here, right? And then we have a azimuthal derivative here, which is sine L5 or cosine L5. So we'll get L times. So we'll get an L outside, right? So the derivative of cosine L5 will be L times sine L5. So we'll get an L out, right? So that term you can see will sort of cancel out with this term, okay, coming from the derivative. So we'll only be left with this Bessel function with higher or lower order, okay? Yeah, this is P naught square. And so there's a question how this happens, right? So to see exactly how this happens, we need to write the boundary conditions just like we did for LP mode, right? So write the boundary conditions, and then so for example, Ez and Hz will be continuous at r equal to a. Then the other field components like ER will be n square times ER will be continuous. So you write these boundary conditions, then you'll get a set of equations, right? Like for example, for the LP mode, we got this J prime over J is equal to K prime over K, something like that. So here the equations will be more complicated, right? Because you can see that so ER and E5 will be complicated, and their boundary conditions matching will be, the equations that we get will be more complicated. So we get transcendental equations again in terms of Bessel functions, but they are now much more complicated, okay? And basically the solution to that equation forces this. Okay? So if you want to exactly see mathematically how this happens, you have to see the transcendental equation. So they are given in a couple of the references. I posted on Moodle in a couple of the books there. Listed out, worked out the whole thing, so you can see for yourself from there. But I don't want to discuss that in class because it's too complicated, and for most applications it's not really relevant. As I said, LP modes work well, but just you should know what the exact solutions are in case you encounter any situation where you need the exact solution. Right? So yeah, if you want to see exactly how this happens, you have to go to the actual transcendental equation that you get. Right. So using these identities for these other field components, we get fields like, for example, ER. Okay, we'll go something like, so if you take a plus sign here, you get JL plus 1. Okay, so this minus sign is important here because that's coming from the derivative of cosine alpha, right? So that minus sign will be important. So one set of solutions will be like this, where ER is this and E phi corresponding to that will be something like this, again with the plus sign. Okay, so this ER and so if we choose a plus sign, we get ER and E phi solutions like this, and these correspond to the EH modes. Okay. If you take the other sign, so ER goes as JL minus 1. Okay, so these set of solutions correspond to the HE mode. Sorry. Okay, so now you can see the transverse field components actually don't. So for the LH order mode, they don't go as JL. They actually go as JL plus 1 or JL minus 1. Okay. So that's a difference from the LP modes, right? For the LP modes, for the LP LM mode, like the EX or EY just went as JL. And another thing is that you have to take into account this phase difference here, right? So you get minus sign here or minus sign here. Okay, and of course you have a propagation part, right? Like so. Right, and this beta again will come from the solution to the transcendental equation. Right? So in general, for each unique LNM, we get a different beta. Right? And the beta for the EH mode will be different from the LP mode. Okay, so we can think about these modes as, so in terms of the ray picture, right? We can think of them sort of as different ray paths through the waveguide, right? Like for example, if you recall the slab, different modes we could think of them as, for example, superposition of plane waves or rays traveling at some particular angles, right? Similarly, in the fiber, we can think of these modes as some kind of rays. So for L equal to 0, they are TE or TN modes, right? So that we can think of as what are known as mediodonal rays, which is basically rays going along the diameter. Okay, so for example, if I draw the fiber here, right? So these rays are basically almost this look like what you would get in a slab. Okay, so they're not really seeing the cylindrical geometry of the structure. Okay, they're just, so this lies in a plane, right? So if you take a cut along the diameter here, this ray is lying along that plane. Okay, so if I look from the front here, for example, so I just see a line like this, right? So the ray going up and down like that. right? So they're just lying in this plane, right? So that's why they are purely TE or TM mode, because you can see that this is basically like a slab, right? I could have basically like a slab here or something. It's not seeing the rotational or the cylindrical symmetry of the structure. The ray is just lying in one plane, right? So the solution, that's why it's either TE or TM, like in a slab. Okay, so these are called meridional rays because they're along a meridian or a diameter. So for L equal to 0. And that's, so L equal to 0, you can see that means no azimuthal dependence, right? So that means, yeah, again, there is no rotational dependence here. It's just seeing, yeah, it's just like a plane. Now for this L not equal to 0, they are known as Q rays. Okay, so they actually have some rotational structure. So the ray will also sort of move around in the azimuthal direction. So it will be like a screw-like movement. Okay, so not only is it just propagating forward, but it's also like it's like going a helical path almost. Okay. So that would look something like this. Okay, so this is like coming out of the board and then hitting the surface in the front. Again, coming out of the board, sort of hitting this surface here, then going into the board, hitting the back surface, and then coming up, right? Hitting the front top part of the back surface and then coming out of the board again. Right? Okay, so it's like screwing around, it's like a helical path. So from the front, if you see from the front side here, they'll have a rotational structure like this. Okay. So as it's going in, it's also like moving in a like helical path. Right. So these are for L not equal to 0. So these are called skew rays. Okay. So this helical motion is what is giving you this azimuthal dependence of the phase, right? Because the phase fronts you can see now, but the wave front now will have azimuthal dependence. Okay. And now if you look at the mode profiles themselves, right? So how do the electric field looks like around the core, right? So they look very different from the LP modes. So one major difference is that the polarization will not be uniform, right? So in the LP modes, we sort of assume the solution to be have a uniform polarization, right, everywhere. But here you can see that ER is position dependent, E phi is position dependent, right? So the electric field vector, the direction which is pointing will also be position dependent. So the polarization will be inhomogeneous. So let's first look at L equal to 0 again. So that will be the TE or TM modes. Okay, so TE01, that will be the first right? So L goes from 0, so 0, 1, 2, 3, M goes from 1, 1, 2, 3, 4. So TE01 will be the lowest order mode, right? So that level null in the center, and the electric field will actually be azimuthal. Okay, so basically, again, that is coming from this either A or B is 0, right? So again, in the expression for ER and E5, we had EZ and NZ, so that one part will be 0. Okay, so then only one of the ER or E5 will survive. So and this null in the center is coming from again. So L equal to 0, we saw that the ER and E5 will be like J1, right? And J1, you know, has a 0 at 0. That's why you get the 0 intensity in the center. So if you look at Tm, so that is primarily the radial polarization and no azimuthal component. So again, so that has a null in the center, but now the polarization vectors point in the radial direction. Right, so again, so here, so for these inhomogeneously polarized beams, you can also see that, so at the center, so what's happening, right? So as you keep going towards the center, so if the electric field is pointing in the radial direction, you keep going closer, closer. So at the center point itself, you don't know what the polarization should be, right? Because at that center point, like it could point in any direction outside, right? Radial direction. So that's known as a polarization singularity, right? So that's why actually you have 0 intensity there. So the way to avoid that is that you get a polarization, you get a null. So in general, when you have these inhomogeneously polarized beams, many times you automatically see zeros in the field just from because the polarization is not defined, right? Again here. So the polarization is E5 as you keep going towards the center, like the polarization, like you get smaller and smaller circles. So at the center point, you don't know where the E should point. So again, the intensity becomes 0. So L equal to 1 is an interesting case. Again, the lowest order will be 1, 1. Right, so HE11, so HE11 actually is almost linearly polarized. There is some slight structure here towards the edges, but towards the center of the curve where most of the power is almost linearly polarized. Okay? Of course, there you have degeneracy again, so it could either be like this or this. Like the polarization would be like that. Right, so recall this looks pretty much like the LP01 mode. Right, so LP01 we had, of course, perfect polarization. Right, and some mode profile like this with no azimuthal dependence, so it's similar like here. Right, there is some small dependence here, right? So, but again, as the index, so this curvature in the polarization becomes smaller and smaller as the index contrast goes down. Okay? So, in the limiting case where the index contrast is very small, approaching 0, then okay. So for these modes, HE11 is the lowest mode. Okay, so it has no cutoff, just like LP01. So HE11 always exists, no matter how small the fiber core is. Okay? Just like LP01 always exists. Right? So HE11 in the exact modes, HE11 is the lowest order mode. Even TE01 and TEM01 have some cutoff, but HE11 has no cutoff. Okay? So that's the lowest order mode. So you can look further, see some profiles for L equal to 2, for example. So if you see it's He21. So now L is 2, right? So we'll get, because of this cosine alpha, sine alpha, we'll get sort of 4 lobes here. Again, there will be a null in the center. Okay, and the polarization sort of, well, yeah, the polarization vectors are sort of like that. Okay, so you can see the field process are much more complicated compared to the LP modes, especially in terms of polarization. Sorry, we're going back to L equal to 1 here. So if you look at He12, so now M is 2. Okay, so that means that there will be a 0 along the radial direction. Again, so L equal to 1 means we'll have J0, right, in the field profile. And J0 means that it will be finite at the center. That's why, so for example, He11 has maximum amplitude in the center, right, unlike these other modes, which has a 0 at the center. Similarly, He12 will also have a maximum at the center because it's J0, but M is 2, so there will be 1 0 along the radial direction. Okay. And then because of this L equal to 1 again, we get these sort of azimuthal dependence. Okay, so it looks like this with a null ring here. So at a particular R, it goes to 0. Because, so again, we have M minus 1 zeros along the radial direction, right, coming from the Bessel function, I mean, excluding the origin. Right, so here M is 2, so we have 1 0 along the radial direction. Right, so this was true also for the LPLM mode, remember. Okay, so yeah, I mean the field profiles for these actual EH-HE modes are much more complicated. And the main point is that the polarization is inhomogeneous. Okay. Right, so basically these LP modes we can think of as a superposition of these EH and HE modes in the weakly guiding limit. Okay. So these two modes are the EH-HE modes, and so basically if we add them up appropriately, we get these LP modes under the weakly guiding approximation, right? So in general, of course, we can't add them up because they are different modes, right? So different EH-HE with different LNM values So EH is different from HE, and also different L and M are different modes, which means each of them have different propagation constants beta, right? So again, going back to this orthogonal precondition of the modes, right? So they're all different modes, and you can't just sort of add them up, right? Because their phase factors will be different. But what happens is that in the weakly guiding approximation, like again for delta very small, the transcendental equations for sort of the EH and HE modes for a particular value of L and M sort of become identical in the limiting case of delta tending to 0. Okay, so that means that their propagation constants will be similar, right? Which means then those modes will become degenerate, right? And then now we can add them up, because degenerate modes we can always add them up to make new modes, right? So any linear combination of degenerate modes is another mode, because they also satisfy the wave equation with the same beta. Right, so let's see how we can think of these LP modes as superposition of these vector modes. Okay, so again, the main point is, so if you have this condition of the weakly guiding limit, right? Then again, if you look at the transcendental equations that you have for the EH and HE modes, turns out that, so if you look at the HE mode with index L plus 1 and the EH mode with index L minus 1, right? So the transcendental equations will have L in them, right? Because we get L already from the azimuthal part, right? And then we put that into the radial part of the equation, right? And then from boundary conditions we get the transcendental equation. So for each L we get a different transcendental equation, right? So if you look at those transcendental equations for the HE mode, the equation for L plus 1, and for EH mode the equation for L minus 1 in this limit. Okay. The transcendental equations become identical. Again, if you want to explicitly see that, you have to go and see the actual transcendental equation. Okay. Which means what? That now basically the HE L plus 1 comma M, so the mth solution of the transcendental equation is the same as approximate size. The mth solution for this transcendental equation. Okay. So now these modes become degenerate. HE L plus 1 comma M and EH L minus 1 comma M become degenerate modes. Right, which means we can take any linear combination of them, and that will also act as a mode with the same beta, right? So for example, so let's take for example this combination, the HE L plus 1 comma M, then add it to the EH L minus 1 with the minus sign, so 180 degree phase. Okay. So consider this superposition. Right, so we know the field profiles we wrote down already. for the EH and HE modes, right? So for example, the ER for this combination now, so we first write for the HE mode. So the HEL went something like JL minus 1. Okay, so HEL plus 1 will go as JL. Right, and we have L plus 1, so the azimuthal dependence will be like cosine L plus 1. Right? Okay, so this is from the HE part. Right, again we have two choices for here. We could either use cosine or sine, but let's consider the cosine solution. Now we take the EH part. So again, EH L had a JL plus 1 dependence, right, for the radial part. So now L minus 1 again will have JL. Right, and again, so here we have L minus 1, so we get cosine of L minus 1. Okay, and then of course the propagation constant now is the same for both. So that is some right. Okay, so this will be now the radial field profile for this superposition. Right, so you can see now we have JL, so that comes out. And then we have now, we can use the cosine rule, addition rule here, cos A minus cos B, to get okay. So we've used that trigonometric identity. Okay. So you can see now we are getting something already like JL times sine L phi, right? So this looks like the LP mode for L. So this looks like the solution for the LP LM mode, right? We have JL and then sine for the ER. Again, we can do the same thing for E phi, right? So E phi. So again, we first take for the HE mode. So if we take this ER, the corresponding E phi was we have minus sine L plus 1 here. Okay, so if we took this cosine here for the ER, then for the E phi we get a minus sign. So this is the for the HE L plus 1 M, right? And now we subtract the EH. Again, if we take the cosine for EH, we have a sine for the E phi. If you take cosine for ER, then we have sine for. Okay, but in this case, sine is positive. Like sine of the sine is positive. Okay, so again, we can use now the another trigonometric identity here. Sorry, this is L minus 1, right? Because this is EH L minus 1. So we get Sine L phi times cosine phi this time. Okay, again, so we used sine A plus sine B. Okay, that identity. So, okay, so we now have E phi, which looks like this, and ER, which looks like this. Right, and now LP mode, recall, were linearly polarized, which means they had, like, for example, X polarization or Y polarization, like a constant polarization in one of the Cartesian directions. Right, so we can express EX and EY in terms of ER and E phi. Right, so for again, we call the coordinate system. So, right, so right, so this is phi. This is ER, E phi, this is EX and EY. Right, so you can see from here EY would be ER sine phi minus E phi cosine phi. Right? EY would be ER sine phi minus E phi cosine. Right, so for this particular superposition, EY would be this times sine phi minus this times cosine phi. Okay, so what will you get? You can see here, so EY, so the JL is common, and then sine L phi is also common. The propagation constant also comes out common, and then you get, so here you have sine phi already, you multiply with another sine phi, so you get sine square, and then minus this you multiply by cosine, so you get a cosine square. You already had a minus sign, so with this minus sign that becomes plus. Okay, so you get this, so this is 1, right? So EY, you see, you get what you have for the LP-LM mode, JL times sine L. Okay, so this is basically the Y polarized LP-LM mode. Right, and you can check that EX will come out to be 0. Right, so it's purely Y polarized, like for an LP mode. Right, so basically what you said is that this combination gives me the LP-LM mode. Right, so in general we can say that the LP-LM mode is some linear combination of the HE L plus 1 comma m and EH L minus 1 comma m. Okay, so remember again, LP mode was four-fold degenerate, right? So instead of X, Y polarized, I could have X polarized. Instead of sine, I could have cosine here. So that gives me 4 combinations. So how do I get the different combinations? Is again by choosing different combinations here, right? So for example, instead of the cos, I could have started with the sine here, right? So that would give me a different solution here, right? And for example, for minus, instead of minus, I could have taken plus. That could have given me one of the different degenerate solutions, right? So I can get the 4 different degenerate solutions by different linear combinations of these HE L plus 1 and EH L minus 1. Okay, so in general, basically, yeah, you can say that the LP-LM mode in this weakly guiding approximation is basically just a linear combination of the HE L plus 1, EH L minus 1, which become degenerate in this approximation. Okay, so specifically, so if I look at L equal to 0, right? So the LP0M mode. Okay, so that the L minus 1 doesn't come into the picture, only the L plus 1 comes in. So this is basically just the HE1M mode. Okay. So for L equal to 0, basically it's not even a superposition. The LP mode is just an approximation of the HE1M mode in this limit. Again, so recall we saw that the LP01 looked almost the same as the HE11, right? So this was LP01 and HE11 had a slight curvature in the electric field, right? So in this limit, this curvature becomes small and it almost looks linearly polarized, right? So again, LP0M is basically the HE1M mode in this case. L equal to 1 is another special case because L minus 1 here, because this becomes 0. So L equal to 0, remember we had TE or TM modes, right? So for L equal to 1, so we have to take either the TE0M or TM0M and superpose it with the HE2. L plus 1 is 2. Okay, so LP1M is a linear combination of either TE0M and HE2M or TM0M and HE2M. Okay, so again, we can take a look at an example. So if I look at the LP11, so recall it looks something like this, right? So LP11. So if I take, for example, X polarized mode, so electric field points in the X direction, there are two lobes. So this is the cosine phi, right? Oh, sorry, this is 0 here and here, so this is like sine phi. Right, so this is the X polarized sine phi solution for the LP11 mode. That can be written as a superposition of TE01. Okay, so TE01, recall, had electric field azimuthally polarized. Okay, so this is E phi plus, again, so TE0M plus HE2M. So that will be HE21, right? So recall that was something like this. Okay, with the center. So now, so if you add these two, so what happens, right? So here, so around phi equal to 0, you can see for TE the electric field is pointing downwards, whereas for here it's pointing upwards. So they cancel out when I add, right? So you get a 0. Similarly, for phi equal to 180, right? So here it's pointing up, here, sorry, this has to point down. Okay. So they cancel out. So again you get a 0 here. And now look at what is happening, for example, phi equal to 90 degree. So here it's pointing towards the right. Here also it's pointing towards the right. So they add up. So you get a field maximum here. Similarly, phi equal to minus 90. This is pointing towards left, pointing towards left. You add up, you get a field maximum. Okay. Now if I take, for example, the negative sign, so linear combination with the opposite phase. Now what happens, you see? So now these places add up, right? Because I'm flipping the sign here, whereas these places cancel out, right? So instead of zeros here, you get zeros here and maxima here, right? So this flips like this. So this becomes like this, right? And now the polarization is like that, right? So here the fields are adding up, pointing in downward direction. Here the fields are adding up, pointing upward direction, right? So now this becomes a y polarized cosine phi solution. For the LP1, right? So again, by taking different, so now if you take Tm, you'll get the other two degenerate modes of the LP1. Okay, so hopefully that's clear how we can think of LP modes as superpositions of the HE or EH modes. Okay, so I think we'll stop here. And next class we'll consider like a graded index fiber, specifically this square law profile that we've seen already in this lab. So we'll see in the cylindrical geometry of the fiber also we can analytically solve for modes in that sort of refractive index profile, and we'll look at how the modes look in that.